Thank you, Mete. It's a great pleasure to be here. I'm very happy to visit again Rio. This is my second time here at IMPA. And I have been lucky because there were some presentations before. In particular, Sylvain talked about game theory. So this is about game theory, but very simple game theory. That's why we can solve it. So very poor game theory. And also, Alejandro talked about this principal-agent problem, and this is exactly what it is about. So I would like to show you how one can use recent development in stochastic control for non-Markovian control systems to solve this principal-agent problem in a systematic way. What I am interested in is to have a solution for this problem which works always. This is the way. This is how to do it. It's like when you have a control problem, you write Bellman equation. That's it. Okay, in which sense, viscosity solutions or not, etc. That's another question. But this is the way to go. So this is what I want to show you. Okay. Oops, this is not working. Okay. Okay, thank you. Okay. Okay, so let's go to the formulation. So this is a stochastic control problem. We have a state equation. X is the state. In this principal agent literature, which is very popular in economics, they call the state process output process. So the output process is X, and here there are two controls. I'm separating the control in two pieces, controlling the diffusion, that's the beta piece, and controlling the drift through alpha, but also beta. There is a reason why. There is a reason why I am writing the drift as in this form, in the image of sigma. You will see the reason for that. So it's not any drift. The drift has to be, there's a structure for this stochastic control problem, and you will see the reason for that. Okay, so controls are alpha and beta, and one important thing is that this stochastic differential equation must be understood in the weak formulation. This is what Sylvain was talking about yesterday. So the way to understand this is that X is a path. So we're working on the canonical space of continuous paths. Omega is the set of continuous paths from 0 capital T to Rd to here it's Rn. D is n in my case. And we are talking about a measure on this set of paths. And on this probability space, xt of any path, this is the canonical process, so it's a projection on the coordinates. This is omega of t. So weak solution means that we want to find a probability measure under which, so P almost surely, the canonical process has this decomposition. So it's a semi-martingale with the drift, which is absolutely continuous with respect to Lebesgue, finite variation process absolutely continuous with respect to Lebesgue, and a local martingale which has quadratic variation, which also is absolutely continuous with respect to Lebesgue, and from there you can draw alpha and beta. So this alpha and beta, in fact, the right notation would be nu equals alpha beta relative to p. So they are induced by p. My solution is p. So this is the weak formulation. And it's very convenient to address this problem. In fact, it's very important, technically also. So the story about this output process is that we want to model moral hazard. Moral hazard is the risk of morality of the agents, meaning that you cannot count on the agents to be moral. You have to give them incentive for morality. This is the story. And in this problem, we will have one agent controlling the process X. So the agent will observe everything, and another agent, which will be called the principal, will only observe the output process X, and is very interested in X. So this is like an employer and an employee. The employer is, the interest of the employer is in the output process, but he doesn't see the effort of the agent. Also, I didn't say in this literature, the control process, they call it effort. So you are employing someone. You don't know how much he's working. You don't know what time he's waking up in the morning. He could be doing nothing. All what you observe is the output of his work, of his effort. So that's the story. So if you observe X, of course, you cannot observe the drift, because the drift is the instantaneous mean. So you have to take the mean under the measure P, but you don't know the measure P. So you cannot observe the drift. You can observe the quadratic variation. But observing the quadratic variation means that you would be observing sigma transpose of beta. But if you observe sigma transpose, you cannot observe beta. Even in the one-dimensional case, if sigma is identity, you would observe beta square, but you don't know whether it's plus or minus 1. Of course, in higher dimension, there is even more imperfect information. Okay, so by observing X, you only have partial observation of alpha. In fact, you don't observe alpha and beta. You can only observe this type of information through the path of X. Okay, so this is the state process. And now agent's problem is written here. So the agent wants to maximize expected value of some discounted value of a salary, Xi, which is called contract in this literature, minus discounted value. K is just a discount factor, which may depend on the control. This is not important. This is just to say that this can be as general as in this formulation. And then there is the cost of effort. Of course, the employee, if he wakes up early, he doesn't like that. So there is a cost for that. This is CT of his effort. There is a cost of his effort. So there is a minus sign. So this is an increasing function of whatever effort he's doing. He doesn't, minus sign means that he doesn't like to do the effort. And as you see here, the only reason why he cares about X, about the output X, the only reason why he cares about the output is because of the Xi here, the compensation depends on X. So this is the incentive which will be given by the other agent. The other agent is going to choose the Xi. So because you receive a compensation which depends on the output, then you would be willing to put some effort. Otherwise, without the dependence of Xi in X, of course, you would do zero effort. You don't care about X in this problem, okay? Okay, so Xi naturally is in the filtration of X. Depends on the path of X up to time capital T. So this notation means this is the path of X of this canonical process of the path. Veg capital T is up to time capital T. You observe the output up to time capital T, and the compensation, the contract must be announced in the beginning between the principal and the agent. The contract is a function of this path up to time capital T. Okay, so this is just recalling the state equation X, and as usual in probability, this canonical process, we usually skip it in the notation. So I'm not writing X anymore. There is no X here. This KT also depends on X. Through the KS may depend on S. The C may depend on X. X is like omega. So usually we don't write omega in probability. Huh?
Why does K depend on the effort? The exponential?
Could be. You can decide not to make it depend on the control. Okay? This is just, it doesn't harm the analysis. You can, I don't know if in any economic problem one can need to do that, but it is not a problem for this, for the general method that I will present. Huh? So again, in here I'm putting X to insist on the fact that this is a stochastic differential equation. X is on both sides. So you really have to solve a fixed point here. But when I write in this formulation, I'm keeping in mind that X is like omega. X is omega. So in probability, we usually don't write omega. Okay? So this is the shorthand notation. Shorthand notation is to forget about the X everywhere. And then if there is a solution to this maximization problem, this solution I call P star of Xi. So this is the optimal response of the agent to the contract Xi. if he is given the promise of a compensation xi of x depending on the effort, then this is the best effort that he's going to do is p star of xi.
C is specific of x.
Typically, but we don't need it. As you will see, it's not needed. In applications, you would take typically C of that form. But for whatever I'm going to present, we don't need a special structure. OK. And again, this discount rate, k, little k, and the cost of effort, C, may depend on x. But I want to write it like this just to insist on the fact that if there is no dependence on x, then the only reason why the agent cares about x is in here. But it doesn't harm. If you could put x here, it doesn't harm the general analysis. OK, so this slide summarizes the problem of the agent. So this is a control problem. Not really standard. The difficulty for this control problem is that the xi is typically path dependent. Of course, you may say, okay, why do you put path dependence in the sigma t of x? You can model this by Markovian system. But again, this doesn't harm. But the most important thing is that the xi be path dependent, because we know in many papers in economics that the solutions which were found for this problem, mainly in discrete time and some papers in continuous time, are typically of the form that the optimal compensation depends on the whole path of x, which makes sense. Why would you pay your employee just on the basis of the final output, where typically you want to look at all the output and base your contract on the whole output? So for example, if the output is very, very volatile, this means a lot of risk. Your employee, you want to fire him before he gets to time capital T. So you should base your compensation so that the output be as stable as possible. Okay? So typically the solutions which are found in the economics literature is that the payment xi of x, the contract xi of x, really depends on the whole output. Okay, so path dependency of xi is crucial and is fundamental in this problem. So the reason why this problem is not standard in optimization, in stochastic control, is that we have this path dependency here. And in fact, once you have path dependency here, as I said, it doesn't harm to put path dependency in the sigma t and lambda t, etc. It doesn't harm. And path dependent stochastic control, my objective since many years, in particular with Mete, is to show that, in fact, these problems should be addressed exactly like Markovian control. And this is what I want to convince you about today, is whatever you know what to do in Markovian control, so you take Mete's book, Stochastic Control of Markov Diffusions, well, you just follow that way and you do it in the non-Markovian case. Well, of course, there is a dictionary. You have to adapt the convenient notions. You have to adapt conveniently the notions, but the way of reasoning, the line of argument is really the same. So this is one of the things that I want to show you today. Okay, so path dependency, the Pontryagin maximum principle approach, it is well known that it's not a Markovian approach. It works in very generally, but it provides a complicated characterization because it's a typically forward-backward system, and typically it's difficult to prove existence, and also it relies on the fact that existence holds. You can write maximum principle by assuming that if there is existence of a solution, then whenever you deviate from the solution, you do calculus of variation. Whenever you deviate from a solution, it is suboptimal, and this is how you get the forward-backward system. Whereas in the dynamic programming approach that I want to base my talk on, in the dynamic programming approach, you don't need existence of a solution. You just start from the value function, and you write an equation for the value function. If you have regularity, then you have access to control, blah, blah, blah. But with very little information, you can have a characterization of the value function. Dynamic programming principle, it is well known that this is not a Markovian concept. Dynamic programming principle, you can always write it, Markovian or not. But what is new is to go to AJB equation. how to go to a JB equation in the non-Markovian case. And in fact, this is now available. It is a little bit hidden in the literature because this is exactly what backward SDEs provide, and also the second order extension that we did with Mete a few years ago. And recently, we are developing viscosity solutions in this context. OK. Let me go back to the problem. I have described the agent problem again. So this agent problem, the main feature, as I said, is the path dependence feature in this stochastic control problem. Now, the other agent, called principal, the principal, as I said, does not observe, has not full observation, only observe the path of x. So he must base the contract only on the path of x. He cannot pay the agent saying that I will pay you that much money if you wake up every morning at 8. It's not possible because he cannot watch whether he wakes up at 8 or not. But he can only base the payment on the basis of the output process, xi of x. So this is the observability problem. And then the principal, what the principal does, his criterion is given by this. There is some utility function here, some discount factor. And then this L, again, there is the canonical process which is hidden. So L is a function of the path of x. So the principal is fundamentally interested in the output. For example, is the owner of the land, and the employee works in the land. He's just working in the land. So the principal really cares about the output. So this is just a liquidation function. It maps omega into the real line just to map it to a scalar. Okay? And of course, the principal must pay the compensation xi, minus xi. It was plus xi for the agent. Agent receives the salary, then the principal pays the salary. So principal pays the salary, benefits from the output, and then there is some crappy utility function, discount factor if you want. That is not important. Okay? And so the game is the principal wants to maximize his benefit from the output, and he's going to incentive the agent by basing the compensation on the path of the output. So he's going to choose optimally what is the optimal contract so as to get the best effort from the agent. Okay? So what you see here is that the principal is going to maximize this criterion by taking the optimal response of the agent. So the principal announces xi. The agent maximizes his criterion and returns an optimal decision, which is p star of xi. And then the principal must do this maximization. Okay, so agent plays first, principal plays second in terms of the game.
Why is L called liquidation?
Excuse me?
Why does L function called liquidation function?
I just called it liquidation because I just want to say that the agent may be interested in the path of x. So if the principal is only interested in the final value of the output, and if the output is one dimension, then that would be one dimensional. It's just the fact that x could be Rn. Okay, so the principal may be interested in many components. It could be vector component of the output. So for example, think about if the production is, if the output is electricity, for example, you may be interested in how much electricity you're producing, but also how much carbon emission you are emitting. It can be vector, okay? Your decision may be based on vector. So it's just liquidating. So in the sense that I'm just converting a vector into a scalar, or if it is the path which is vector valued, I want to convert that into a scalar. So okay. Now there is one important feature here is that this maximization is over this class of contracts. So again, the class of contracts is a filtration of x. So this means that xi is a function of x only, of the path of x. So the principal reduces to those x's so that p star of xi exists. So he sends a contract to the agent so that he knows that the agent can return an optimal decision. Well, we haven't done it, but I suspect that we can put epsilon optimal here. One should be able to have a relaxed version, but we didn't do it. There is some integrability. I don't want to enter through that. We will see through the talk which kind of integrability we need. And more importantly, there is this participation constraint. Without this participation constraint, what the principal can do is to pay the agent minus n. Okay? Then by paying minus n, it becomes plus n here, and you can send n to infinity, and formally you get plus infinity from this principal problem. And for the agent, if he has to take this minus n, the poor agent will just maximize this criterion, return an optimal decision, and that's it. And he's going to pay minus n. Of course, this is not realistic. And economists add this participation constraint. They say that the agent can say, no, thank you, I don't participate. I don't sign the contract. If he doesn't get enough in terms of value function, he says, no, thank you. I prefer to stay at home, not to work. Okay? So this is a participation constraint. Without this constraint, the problem is completely degenerate, as you see. R could be anything. Huh? So it depends, of course, on the function, on these functions here. If you, well, here also xi can be negative here. Xi can be negative. Huh? This is one of the issues that economists raise. Of course, if you sign a contract with an employee telling him you're going to pay $10,000 at the end of the month, he will not agree. Yeah? So that's one of the non-realistic things, and that's one of the things that we can do with this approach. I will show you. Okay. So it's very present in everyday life. In the insurance sector, fully insured drivers do not have incentive to increase caution. This is why you have bonus and malus. I don't know if in Brazil you have this, but if you, yes, if you have an accident, you pay your premium more expensive. This is to make you more responsible about your behavior. Health insurance misleadingly lowers out-of-pocket expenses and thus increases demand for medical services. If you pay some part of the drugs that you buy, then you would buy less. Of course, this is economist rationality, not caring about social effects. Huh? This is very, very capitalistic type of arguments. Unemployment insurance may give negative incentive to return to the job market. This is a big issue in France, for example. And this picture, if you can have an insurance on speeding tickets, then you can imagine what can happen. Huh? So this is a fake advertisement. For those who are familiar, these type of numbers do not exist. 1-800-555 does not exist. Okay. So these are examples in insurance, but you can think about many, many examples. I just picked this picture because this is a popular subject now. It's financial regulation. And we have been talking a lot about moral hazard in finance, about the way compensation of traders is computed, and the fact that if traders are only, the incentive of traders is only on how much they make, then they will take a lot of risk. So their compensation should be also towards the incentive of letting them take less risk. So this is also a subject which can be addressed with this type of tools. Okay, existing literature. It's a very old subject in economics. Moral hazard was introduced, identified already by Adam Smith as one of the main risks in economics. It is very, very developed in the economics literature. From the point of view of game theory, this is a non-zero sum Stackelberg game. Agent plays first, principal plays next. I'm not writing anything about discrete time formulation because I have to confess that I'm not familiar with that, but there is a huge literature in discrete time. I was told that the first paper was by Mirrlees, but you were citing another one. So, Meyerson? It's Meyerson, not Mirrlees. I thought it was Mirrlees. Meyerson, okay, thank you. Now, the continuous time literature started from this paper of Horstrom and Milgram in Econometrica 87, where he was addressing one particular example. And all over this literature, there is no control of the diffusion. No control of the diffusion. So if I go back to this, to the formulation of the problem, maybe I go back to, there's a slide where everything is summarized here. Yes? So the beta is not there. There is no control of the sigma. And there is one fundamental difficulty with putting control on the sigma, because in the weak formulation, for different betas, you produce singular measures. So these measures have singular supports. So there is a fundamental mathematical difficulty coming from there, because zero measure null sets become important. Where typically in probability, we always start by hanging an omega fp on the top of the blackboard, and then whatever we do is p almost surely, and nobody cares about null sets. Whenever you put control on the diffusion, null sets become very important, because null set for one measure can become full measure set for another one. And it's a cause of a lot of trouble. So one of the objectives is to extend to this case. So in the economics literature, there is no beta. They only control the drift. They only control the drift. And there are many applications where controlling the sigma is important. For example, in portfolio management, you typically control the sigma, because by choosing the portfolio strategy, in fact, you are changing the sigma. That's one possible example, but there are many, of course. Okay, so in the economic literature, only control of the only uncontrolled diffusion, and also all the examples that I have seen are based on explicit solution. So typically, they take one-dimensional state, and typically they would take infinite horizon. Then the Bellman equation becomes just an ODE, and then you can hope to find an explicit solution. And if you look at the literature, it's always in that context. And usually, once you have an explicit solution, you can have some way to prove it. It's much easier when you have an explicit solution. So our objective is to have, as I said, a general solution. You don't need to rely on explicit solutions. And in particular, we can go away from the one-dimensional case. There is another direction of the literature, which was started by Jakša Cvitanic, by co-author in this project. And what Jakša started to do is to use calculus of variation. So assume that there is an optimal contract, and then do calculus of variation out of that. It's very, very heavy technicality. It is also restricted to uncontrolled diffusion. And at the end, you get the so-called Pontryagin maximum principle, which is typically forward-backward system. And it is very difficult to have a well-posedness of this forward-backward system. So they have some examples that they can solve like that. In general, they just have forward-backward system, and they cannot even formulate under which conditions you have existence and uniqueness. And again, that's important because you are assuming existence of an optimal contract. You get a system of forward-backward equation for which you don't know existence, so you cannot go back. It's not closing. Okay, there is a book by Jakša and Jianfeng Zhang on this. This is a very good book based on this Pontryagin maximum principle. But what I like about this book is that you can understand the notions. If you go to read the economics papers, at least for me, it was very, very difficult to understand what's going on. Typically, economists, they do not formulate the problem. They know what they are talking about. They know in between them, but they don't write it. It's not like the mathematical tradition where you write the optimization problem very precisely. So in this book, they did this effort of reading precisely the economics and picking up the right definitions. So then you can do the math. Once you read this book, you can go to the math. Okay. So our objective, I have been very long in this introduction. Our objective is, as I said, simple and systematic solution by standard dynamic programming. And it's inspired from a paper by Sannikov. Sannikov is professor at Princeton, economics professor. And this paper, again, is very difficult to read, but it's very, very inspiring. And in fact, the solution is in that paper, in the case of control of drift. It's not correct technically, but who cares? The idea is brilliant. In this paper contains a brilliant idea. You can make it correct. So we want to, as I said, include diffusion control. Dimension of x doesn't matter. And we don't need to have explicit solution. And in fact, as you will see, we will have a PDE, so you have access to numerical approximation. So you can just formulate a problem, have a PDE, and go to numerics. And also possibility to include additional features, e.g. like limited liability. So limited liability is related to what I said before. Limited liability is the question that you cannot ask the agent to pay negative price. And in fact, to pay negative price is not about disk C. What economists wants to say is that negative price for them is the value function of the agent. You cannot ask the agent to have a value function which is negative at any point in time, which means that from the mathematical point of view, which means that you should consider the continuous time, you should change the origin of time at time t, as usual in dynamic programming. And then at any time t, if you look at the dynamic problem, the value function of the dynamic problem should be non-negative or greater than something. And for us, it's going to be just a state constraint. And it seems that this problem is open in economics, and they don't know how to do it. And with this approach, it becomes just a state constraint in PDEs. Okay, so, okay, enough talking. Let me show you, yes?
I mean, about this non-negativity at any point in time,
yes.
I could think of situations where a firm is about to go bust and then the employees should, I don't know, not receive a salary or maybe even chip in, and then they save the company somehow and the company gets back on its tracks.
Okay, but there is always a lower constraint. Lower bound constraint is always there. You cannot ask someone to pay minus 1 billion because the employee doesn't have it. Huh? Yeah, it could be any state constraint. Okay. Of course, zero is not important here because you can put utility function, whatever. You can add a constant. It doesn't matter. Okay, so how to solve this problem? As I said, you read Mete's book, Stochastic Control of Markov Diffusion, and you do whatever you know how to do in Markovian case. You just copy it in the non-Markovian case. So the first thing to do for the agent problem, this agent problem, if it were Markovian, if you were to write the dynamic programming equation for this problem, you start by writing the Hamiltonian. Hamiltonian is the usual crap here. So it's you take the generator of the diffusion. So this is the drift multiplying the gradient. Z stands for the gradient here, plus 1/2 diffusion squared trace with the Hessian matrix. Gamma is going to be the Hessian matrix everywhere. Then there is a cost, running cost, minus C. There is a discount factor, minus Ky, Ito's formula. This comes from Ito formula. And it's a maximization problem, so maximize over controls this linear generator. Right? So the only difference with Mete's book, again, is that instead of writing little x here, which would be a finite dimensional variable, I'm writing a path, omega. Okay? So now it becomes a stochastic process. The dependence on omega is non-anticipative. Okay? But it's just copying whatever we have been doing for years in the Markovian case, copy it in the non-Markovian case. Now the next trick, which is very easy, is to introduce this process. So give me two processes, z and gamma. So this is now capital. This is a variable, little z, which will stand for the gradient. And now I'm taking a stochastic process, capital Z, which has the same dimension. So this is a stochastic process with values in Rn. And give me another process gamma, so this is capital gamma, so it will have values in the matrices of size n, symmetric matrices of size n. So give me two processes like this, which are in the filtration of x. So it depends on the path of x. This is very important because I will state a result which will take this y capital T z gamma as a contract. And of course, the contract must be in the filtration of X. So I need all the components to be in the filtration of X. This integration, the dxt is in the filtration of X, so I need the z to be in the filtration of X. This is quadratic variation that I can read off from the path of X. This is the Haitian, but now I'm assuming that this is in the path of X. And this is my Hamiltonian that I'm using here. Okay? And I would like, there is one thing important here is that I would like this yz gamma to be defined P almost truly for all P in my admissible dynamics. So unlike stochastic integration, here I'm doing stochastic integration simultaneously under a family of singular measures. There is some technicalities there. No? So it's a little bit away from the standard stochastic integration. So we have to define all these things, not only P almost surely, but we need to define them P almost surely for all simultaneously under all these probabilities which have singular supports. So we have to be careful with zero measure sets. Okay. The only difficulty in here is that y appears on both sides because z and gamma are given. Huh? Y appears on both sides. It's a random ODE. It's an ODE with random coefficients. So whenever h is Lipschitz in y, we are fine. And this is the case. H is Lipschitz in y because I'm assuming that this guy is bounded. K is bounded, then I'm fine. So this h is, so existence for this y is not an issue. Okay? So this is, again, this is a definition. I introduced this Hamiltonian, exactly like in Markov-Keynes. I introduced this process. Now, with this specific form, we can prove the following. We can prove that. So remember my notation. This is the value function of the agent parameterized by Xi, by the contract. So what is said by this proposition is that if I take as contract Xi equals y capital T, then I know exactly what is the value function. It's y0. I know exactly what is the value function. It's y0. y0, remember, I decided what is y0. So somehow I'm saying if I decide for this type of contract, then I know exactly what is going to be the value function of the agent. So in particular, the constraint, the participation constraint, is y0 greater than capital R. Okay? So not only y0 is known, but also any solution, the solutions are characterized by the classical maximization of Hamiltonian. And therefore, the dynamics of the state process under the optimal decision of the agent are just given by these dynamics, where what is this? This is the drift using the optimal control deduced by maximization of the Hamiltonian. So if I go back to the H definition, if I want to identify the drift, this is sigma lambda, I take the gradient with respect to z once I take the soup. This gives me the optimal drift. Okay? And if I want the optimal diffusion, I should take the gradient with respect to gamma of the capital H. Subgradient. Okay, subgradient. Who cares? Huh? Okay? It's almost everywhere is the gradient. Huh? Everything is convex there. Huh? So I have to take the gradient with respect to this gamma, but this there is a 1/2 there. There is a 1/2 there. So this is the reason why I have a 2. Okay? And there is a mistake. I should be taking square root of this. Right? Because it's sigma transpose. I should be taking square root. There is a mistake. This should be square root. There is a square root at the end. Okay? So this is a 2 lines proof. This proposition is 2 lines proof, and I can show you very quickly why this proposition is correct. So let me do it in the case where discount factor is 0. It's not important. Huh? So I want to look at the value function of the agent when Xi equals y capital T z gamma. This is what I want to do. Okay? So by definition, the value function of the agent is expected value for any p. I need a p also. For any p in my admissible dynamics, this is expected value no discount factor, so I should write xi here, minus integral of cost of effort, right? Nu t dt. Okay? And xi is y capital T z gamma. Y capital T z gamma, there is a constant y0. Then there is this stochastic integral from 0 to t of this zt dxt. There is this 1/2 of gamma t. Quadratic variation of x is exactly sigma sigma transpose dt. And finally, there is the h minus ht, right? So let me erase this integral minus this, and then let me continue here. Minus, so this is dt, minus ht of whatever yt, zt. Again, I don't write omega. X is omega, gamma t, dt. Now you see what happens. The dxt is, there's a drifter. This is sigma lambda dt plus sigma dwt, and this is a Brownian motion under P. So once you take expected values, and once you sit on local martingales, but this is just technicalities, you are just left with the drift part, and then this is now exactly what you find inside the maximization of capital H. So what we read here is something minus the soup over all possible controls. This is the usual argument in verification in control theory. So this is always negative. Now this is always negative. And the only way to make it equal to 0 is that whatever is inside the integral equals to 0 p star almost surely, if p star is optimal. Okay, so that's the proof of this proposition, very easy. Huh? So it's just the classical verification argument. Okay, so this is how we get this. And again, this is just to write things like what we used to write in the maximum Pontryagin principle. Okay, now with this result, we immediately have this lower bound, which says that the principal problem is always bounded from below by principal problem is the soup over all possible contracts. So if I restrict myself to this particular contracts, yt z gamma, then of course the soup is going to be lower. So this is all what is said here. The principal problem is always bounded from below by this soup. So this is because this is the participation constraint, y0 greater than r, and this is the value function if the contracts are restricted to this yz gamma. And this value function is soup of expected value under the optimal p hat z gamma, which is obtained by maximization of h, so as to make this equal to 0. And this is exactly what is written here. So notice that in this maximization problem now, this v lower bar problem, we have two state variables. We have the x and the y. The x is the dynamics in the previous proposition, and the y is precisely my definition of the y. And I'm back to a standard stochastic control problem. Now, v lower bar is a standard stochastic control problem. There is no game anymore. So for this problem, I can write Bellman equation, etc. Okay? So this is why this problem, v lower bar, is nice. Now I'm back to standard theory. Back to Mete's book. Okay, you can do numerical methods, no matter what is the dimension of x, etc. You can do it in higher dimension. And it's systematic. You can always do that. And if you have the liability constraint, again, that I was talking about, the limited liability, y greater than 0 or some lower bound, y is exactly the value function. This is what is said by this proposition. The running value function is y. So if you look at the dynamic problem, it's going to be yt. So this limited liability constraint is just yt greater than some bound. So it's just this control problem with the state constraint on y. So many problems now can be addressed with this formulation. Okay. Now, the reason why I'm giving this talk is that Not only this is a lower bound, but there is equality. So in fact, the principal problem equals this soup. We are not losing any contracts by doing this. There is no loss. All contracts are of this form or can be approximated of this, by something of this form. Of course, because I'm going to take the soup. So for the soup, I can have approximations. Okay? Why is this correct? So if I have to prove this, the first attempt is to say, can I write any XI, any contract in this form? This is a representation result. You give me a random variable XI which has certain integrability, and what you ask me for is, can you find Y0, Z, and gamma so that XI can be represented in this form? If I can do this, then I'm done, of course. This means that I'm not losing any contract, and equality holds, okay? But in fact, I can do it with less f, with less than this condition by verifying that I can find an approximating sequence. If I can find Zn gamma n, I can approximate any Xi like this, and I can pass to the limit in the principal problem, then I can make it. Okay, there is one case. Let me, I don't know how much time I have left. Oh, okay, 2-3 minutes, right? Okay. Let me show you one case which is very easy, in which we can prove this representation. Let's go to the case where there is no, yes? This is taken on my time, huh?
Yes.
No, I said that sometimes it would be easier just to characterize the boundary and to say that if the contract doesn't satisfy this condition, then they find another one that's better.
So
But you don't want to show that all contracts can be of this form.
okay, yes, you can go from above, of course. In this approximation, yes. All you need is you can go higher with the approximation. Yes, of course, yes. That's right. Okay. Now let's look at the case which were looked in the literature, no diffusion control. If there is no diffusion control, then in the Hamiltonian, remember Hamiltonian is a soup over controls. Now the sigma does not contain any control, so the sigma gets out of the Hamiltonian. Okay? The sigma part, 1/2 of trace sigma, sigma transpose gamma, gets out of the Hamiltonian, and you're only left with the maximization over the drift, the discount factor, and the running cost. Okay? Now in this structure, if you go back to yz gamma, the representation that you're searching for, Xi equals ytz gamma. So let's write again, y0 integral of z dx plus 1/2 of gamma dxs minus hs blah, blah, blah. And now in the dependence on gamma is exactly factored out like this, but the quadratic variation is exactly sigma, sigma transpose. So these two terms cancel. So you are reduced to this problem. There is no gamma anymore. So in fact, when there is no control on diffusion, you want to solve Xi equals y capital T z, where y capital T z is this type of representation. And this is a known problem. This is exactly a backward stochastic differential equation. If you look at the problem now like this, I have a random variable Xi, which is f capital T measurable, and I want to write it in this form. If there is no f, this is the martingale representation theorem. It's the heat equation in PDEs. And with an f, it's a Picard iteration of the martingale representation. This is exactly like also Sobolev solutions in semi-linear PDEs. It's exactly the same proof. So you find a fixed point in some LP space, p strictly greater than 1, and that's it. So in this case, the representation holds. And notice that in this case again, if sigma is not controlled, then remember we have to have a representation p almost surely for all p solution of the SDE. So these are singular measures. But if the sigma is not controlled, all the measures are equivalent. That's Girsanoff theorem. So in fact, I need to solve this problem under one single measure, p0 almost surely. So it's exactly BSDs. So it's much simpler. And this is why going to the nonlinear case is more complicated. Going to the nonlinear case is a little bit more complicated, but in fact it is, one can do it. Unfortunately, I was planning to give you some hint on the solution. But it's based on this result. This is a previous work with Mete and Jianfeng Zhang, which was improved by Dilan Posamai, Xiaolu Tan, and Xiao Zhu, which have been all PhD students in my group at the same time, and they defended their thesis the same year. So they are still good friends. And they did the hard work of extending my paper with Mete and Jianfeng, because in our paper we had lots of technical craps. Because of these singular measures, then we were assuming that this Xi is in the closure, in a certain closure of uniformly continuous maps. Uniformly continuous in terms of omega. This is not a nice assumption, but we had to do that to prove this theorem. And what Dilan and Xiaolu and Xiao did is to prove that, in fact, this holds for measurable Xi just under antigravity conditions. And this is exactly what we need to solve this problem. We have this representation result. And with this representation result, we can prove that we can approximate Xi by a sequence Xn, which does the job, which has the right representation. OK, so I will stop here. Thank you very much for your attention.